Okay, welcome. This time we're going to try to point the arrow of time and try to think about what that is. This is part of Extraordinary Concepts in Physics. I'm Robert Nemeroff, a professor at Michigan Tech, and trying to come up with the fun topics and talk about them for anyone who's interested, but there are physics students taking this class. There's lots of these lectures. You can find them on iTunes or in Starship Asterisk. If you go to Starship Asterisk, you're able to actually resolve that web address, and you can find slides. All the slides ever given in this course are there. Arrow of time. So let's start out with some concept questions, which I like. So you look at a movie of two particles colliding. Probably not a blockbuster. The two particles go in and two particles go out. Is it possible to tell whether this movie is being shown forward or backward in time? Can you tell that? These are the things that people think about that I've thought about for a while. Is the arrow of time unique? So the possible answers could be no. No. The movie will look normal either way. Yes, the movie run backwards would look strange. You don't even have to understand how strange, it would just look strange. And we did this once in elementary school and everyone laughed. Answer is no. The movie would look normal either way. Microphysics involving individual interactions is time reversible, which means that if you get into the math and you have lots of equations, just replace every time you see t with minus time. And the equations are usually just as valid. It is not possible to tell the direction of an arrow of time from seeing two particles collide. So if you wanted to drill into this a little bit deeper, which isn't that important, but you can a key concept in this is the conservation of mechanical energy. So according to Noether's theorem, which is a really cool theorem come up by Noether, a system that conserves mechanical energy is time invariant. And that's an important underlying principle here. But let's get back to the next movie on our hit parade. Rated by Rotten Tomatoes is the second most popular movie of this lecture. You look at a movie of a ball rolling down a hill. The ball starts from rest and increases in speed. Not very interesting, or is it? Can you tell from this movie which direction time is running? No. The movie will look normal even if run backwards would be answer number 1. 2, yes. The movie run backwards would look strange because balls don't roll up hills. 3, time doesn't run, people run. Get this straight. That makes all the difference. So you can contemplate this now, turn it off, go have lunch, ask your friends, phone a neighbor. Drum roll. No, movie would look normal even if run backwards. How can that be? Balls can't roll up a hill, but they can. Consider that after the ball rolls down a hill, there's another hill. So let's say there's a hill here, and there's another hill there. And so you had a ball here, and it was rolling down the hill, and you saw the movie from here to here. But the ball kept going, and then it rolled up another hill. And if you ran the movie from here to here, it would look the same. So if you only saw the last part of that movie, it would seem normal. So one can't tell the arrow of time even using simple gravitational systems. You don't know which way the movie's running. You don't know. Why can't we remember the future then? If all these physical equations look the same backwards and forwards, if every movie looks the same, how come we can't remember the future? Now, psychics and physicists spend significant effort trying to predict the future. My experience is that psychics are wrong a lot of the time, unless they're really vague. Physicists make actual useful predictions, such as how strong you can make your building, how many people you can have in your building, and how fast cars can go, as opposed to who's going to get married. No repeatable experiment has ever been shown that anyone or anything has the ability to remember the future. So there seems to be a strong barrier between the past and the future. So there seems to be a real arrow there, but we haven't uncovered it yet. It's not really known why, but pay attention. There might be some interesting thoughts here. So we go to the third movie. Now, in this movie, you see an egg rolling off a table and cracking open on the floor. Don't worry, who's going to clean it up? Would you be able to discern an arrow of time by comparing this movie with the same movie run backwards, where the egg reconstitutes itself and jumps off the floor and ends up on the table? Yes, duh. No, double duh. And only if the anti-egg is unitarily cross-temporal. So we can choose between these. So we used to have a game where we would just give physics gobbledygook babble sometimes and try to make things sound like you really know what you're talking about. So I'm somewhat experienced in this. Sorry. Yes, duh. So, but it's a profound duh, so you don't feel too bad. A broken egg is arguably in a higher entropy state than a whole egg. In other words, there are many more ways an egg can be broken than an egg can remain unbroken. The second law of thermodynamics says that for closed systems, entropy must increase on the average. So the arrow of time points from the unbroken egg to the broken egg, and we know which way the movie must run to appear normal. So we finally found a movie you can watch, but it doesn't appear to involve individual particles interacting with microphysics. So there are, people think, a bunch of physical processes that might define an arrow of time, where an arrow of time means you know which way to run the movie. Thermodynamics and entropy, like just shown. Cosmology and the universe expansion might. The universe is expanding now, so you just point the arrow of time and the universe is still expanding. Radiation and a stone in a pond. If you throw a stone into a pond, you see circles emanating from it. You should be able to know which way that goes. Cause and effect, more general. You know something causes something else. You have knowledge of that. Shouldn't that orient the arrow of time? The weak nuclear force and kaon decay. Oh, hadn't thought of that. But that actually turns out to be of importance. Quantum mechanics and wave function collapse. Mentioned, if you're really paying attention in other lectures, you might have heard that mentioned before. Psychology and memory. Let's talk about cosmology. So we talked about the first one already, entropy. The expansion of the universe defines an arrow of time. In the present epoch, the future can be discerned from the past since the universe expands into the future. Some feel this outside of entropy defines an arrow of time. It has been suggested, though, that were we in a closed universe that had enough mass so that it would begin to recontract, the arrow of time would reverse. If so, then we're confined to be in a universe that always expands. So even if the universe expands and contracts and expands and contracts, oh, why does this happen? Excuse me. Then we can only remember the ones where it's expanding if the arrow of time only points in that direction. As I mentioned, watching cause and effect might define an arrow of time. Again, people think that every time you look at this, and some people think that every time you look at this in detail about causality, it gets back to entropy, and that cause and effect is ultimately defined statistically with higher entropy systems. The weak nuclear force and weak particle decay. So it turns out that if you watch some particles decay, they decay through an unusual thing called the weak nuclear force, beta decay, something like that. So this breaks symmetries. For instance, this breaks left and right symmetry. So previously in physics, what decayed to the left could have decayed to the right for all anyone knew. But with a weak nuclear force, it actually has a preferential direction that it wants to decay. Also tied into this asymmetric decay is that it defines an arrow of time. That you can only decay in a certain amount and get a certain way. Things have to decay so that the decay defines the future. Undecayed, past. Decayed, future. Kaons exhibit this, a type of particle. Mentioned before, wave function collapse. So particularly in the Copenhagen interpretation, whenever you measure something, so a photon could go through a pair of slits, as was gone through by something like six lectures previously. However, when the photon is actually measured, it's hit the detector, then that wave function of the photon collapses. That's not a reversible process. So the search for the arrow of the time is the search for processes that are not time reversible, and the collapse of the wave function could be. However, there's been a lot of work on quantum decoherence recently, and some people are beginning to think that quantum decoherence, which is sharing energy with the outside universe, or letting the outside information seep in, is essentially entropic. It's really possibly no different than the entropic arrow. This is something that people are investigating right now. It could be that we really only have one arrow of time, and that's entropic. All of these might have been tied into entropy. Actually, surprisingly, that was my last slide on this. So actually, in future lectures, we'll get into time travel, which obviously involves an arrow of time. But so far as we know, we can't remember the future, we only remember the past. Exactly why is not known. It might be tied to entropy. And with that, I will leave you toward next time. Contemplate the arrow of time.